In today's tutorial, I will provide solution to this given problem. We have to prove that the root of the equation x squared plus k minus 2x minus 2k equals to 0 are real and distinct for all real values of k. Okay, so this is what we are given. Okay, and we have to prove that the root of the equation are real and distinct for all real values of x. And of course, for discriminant of quadratic equation, we have real and distinct roots, we have real and repeated roots, and we have no real roots. For real and distinct, of course, the discriminant d, which is given to be b squared minus 4ac must greater than 0. That is for real and distinct. Okay, and of course what we need to do here is to compare the given equation with the general quadratic equation, which is of the form ax squared plus bx plus c is equals to 0. So by comparison now, we have a to be 1, then b to be k minus 2, and of course we have c to be minus 2k. So now all we just need to do is to substitute these constants to the equation where you have b squared minus 4ac greater than 0. So by the time you substitute that into the given equation, so we have k minus 2 all squared minus 4 in brackets of 1 times minus 2k then greater than 0. And of course we have k minus 2 squared, and this will give us minus 4 times minus 2k, that will give us plus 4k greater than 0. Also, the next thing to do is to expand k minus 2 squared, and of course when you expand that, that will give us k squared minus 4k then plus 4 plus 8k greater than 0. Alright, so we are rearrange where you have minus 4k plus 8k, that will give us plus 4k. So we therefore have k squared plus 4k plus 4 greater than 0. So okay, the next thing to do is to factorize this. Alright, is to factorize this. So let's factorize this. We have k squared plus 4k plus 4. Product of 4 and sum of 4, we make use of 2 and 2. So k squared plus 2k plus 2k then plus 4 greater than 0. Okay, so from the first two terms here, I mean this place and this, we can actually factorize k out. So you will left with k plus 2. And for the last two terms, which happen to be 2k and 4, the only thing that is common there is 2. When you factorize 2 out, then you have k plus 2 as well, greater than 0. And of course, k plus 2 is common, we factorize that out. And here we have k plus 2 greater than 0. So what will now happen now, the whole of this expression can be written as k plus 2 all squared greater than 0. Okay, and of course, since we are to prove that the root of the equation, the value of the k here that will satisfy the equations are real for all values of k, okay. So when you look at this, remember we are given that the condition here is given to be real and distinct. So for all real values of k, now to do this now, how can you find the value of x here? K, we are given that k plus 2 squared greater than 0. Okay, for k plus 2 squared greater than 0, irrespective of the value of k, that means whatever result you obtain here, be it positive or negative, by the time you square that, we eventually have positive results. That is why k plus 2 is greater than 0. And now, irrespective of the value of k, okay, if k plus 2 squared is greater than 0, that doesn't justify that k plus 2 will also greater than 0. No. Okay, it is not true at all time. But for k plus 2 squared to be greater than 0, that means irrespective of the value of k that you put here, square of that must be what? Positive. So which implies that the value of k belongs to what? Real numbers. So, and this can be written as minus infinity to infinity. So which shows that for every value of k you put here, we are going to have positive results. Okay, so that is that. If you are just joining us for the first time, don't forget to click on the subscription bell so that you'll be notified whenever I release new video. Thank you.